I'm Rajesh Uppal, Director IDST. We bring sharp insights and foresight on defense, security, and emerging tech. Let's dive in.
Imagine something no bigger than a shoebox, orbiting hundreds of kilometers above Earth, conducting science experiments, taking high-resolution images, and even exploring deep space. These are CubeSats, small, modular satellites that have completely changed how we access space. CubeSats are fast, affordable, and versatile, allowing universities, startups, and even high school teams to launch missions once reserved for billion-dollar spacecraft. But for all their promise, one challenge has always held them back: propulsion. You see, most CubeSats are passive. Once deployed, they drift in orbit with little control over where they go. Without propulsion, they can't dodge debris, maintain formation, or change orbits. They simply ride until gravity pulls them down. But that's changing, fast. Engineers are developing miniaturized propulsion systems that can fit inside a CubeSat's tiny frame. These thrusters are unlocking new capabilities, from fine-tuned orbital control to long-distance navigation, turning CubeSats into agile explorers capable of much more than before. So, how do these propulsion systems work? Let's break it down. Some of the simplest are kinetic propulsion systems, like cold gas thrusters. Think of them like tiny air cans for space. They store compressed gas, usually something inert like nitrogen, and release it through a nozzle to produce thrust. The idea is simple, reliable, and safe. But there's a trade-off. These systems don't generate much power, so they're mainly used for small adjustments in attitude control, not for major orbit changes. Then there's chemical propulsion, which delivers raw power. These systems burn chemical propellants to create thrust, giving CubeSats the kind of muscle needed for rapid maneuvers or deep space missions. Traditional fuels like hydrazine are effective but toxic, so scientists are moving toward green propellants, such as AF315E or LMP103S. These are safer, cleaner, and just as powerful. They allow CubeSats to reposition in orbit, avoid collisions, or even escape Earth's gravity without endangering the people who handle them. Next up is electric propulsion, the sleek, futuristic cousin of rocket engines. Instead of burning fuel, these systems use electricity to accelerate charged particles, ions or plasma, to create thrust. Imagine a slow but steady push that keeps going for months or even years. Electric propulsion systems like ion thrusters, Hall effect thrusters, and electro-spray thrusters are extremely efficient, delivering long mission lifetimes using minimal fuel. One of the most exciting of these is the electro-spray thruster. It uses charged liquid droplets to produce incredibly precise, gentle thrust, perfect for small satellites that need to maneuver delicately without wasting power or fuel. NASA's Lunar IceCube mission even tested this technology, proving that these mini thrusters can operate reliably in the harsh conditions of space. Still, every technology has trade-offs. Electric systems are efficient, but they need a lot of electrical power and produce low thrust, which makes them ideal for long, steady missions, but not for quick moves. That's why engineers are experimenting with hybrid designs, combining the best of chemical and electric propulsion for flexibility and control. Now, let's talk about water-based propulsion, one of the most creative solutions yet. These systems use ordinary water, split into hydrogen and oxygen through hydrolysis, and then recombined to create thrust. It's safe, simple, and sustainable. And because water is abundant in the solar system, on the moon, asteroids, and Mars, future spacecraft could literally refuel themselves from space resources. It's a small step toward long-term, reusable exploration. There's also a new class of non-propellant systems, like solar sails and electrodynamic tethers. Instead of carrying fuel, they use natural forces, sunlight and magnetic fields, to generate thrust. Solar sails work by reflecting photons from the sun, gently pushing the spacecraft forward. Electrodynamic tethers, on the other hand, use electric currents interacting with Earth's magnetic fields to move or slow down a satellite. These systems offer virtually unlimited operational lifetimes, perfect for long-term observation or debris cleanup. And the innovation doesn't stop there. New propulsion concepts are emerging that sound straight out of science fiction. Microcathode arc thrusters, for example, vaporize bits of solid metal to create precise bursts of thrust, ideal for the smallest CubeSats. Laser and microwave propulsion takes it even further, using beams of light or energy from Earth or space stations to push satellites without carrying fuel at all. Meanwhile, 3D printing, or additive manufacturing, is transforming how thrusters are built. Engineers can now print lightweight, customized engines with integrated cooling channels and optimized shapes that were once impossible to manufacture. This not only reduces cost and complexity, but also speeds up development for new missions. Many of these technologies aren't just theoretical, they're already flying. Missions like CanX-4 and CanX-5 have demonstrated formation flying with cold gas thrusters. NASA's Marco CubeSats used micropropulsion systems to navigate all the way to Mars. And with green propellants and 3D printed systems entering service, we're witnessing a revolution in miniature space mobility. Still, the road ahead isn't without challenges. Power supply remains a major constraint, especially for electric thrusters. Some propellants are difficult to store or handle safely, and miniaturizing components while keeping them reliable requires cutting-edge materials and precision engineering. But the progress is undeniable. Each generation of CubeSats is more capable than the last. Looking forward, the future of CubeSat propulsion lies in hybrid systems that combine multiple modes of thrust: electric for efficiency, chemical for quick bursts, and AI-powered control for autonomous decision-making. Imagine CubeSat fleets navigating deep space, adjusting their formation on their own, powered by solar energy and guided by artificial intelligence. Propulsion is no longer an afterthought in CubeSat design. It's the key that unlocks their full potential. These tiny explorers are proving that innovation doesn't have to be massive to be meaningful. In the coming decade, CubeSats equipped with next-generation propulsion will explore the moon, asteroids, and beyond, transforming space from a distant frontier into a living, dynamic ecosystem of discovery.
Thanks for watching. Subscribe, follow, or visit idsth.com for more cutting-edge defense and tech insights. See you in the next one.